Yesterday, we were talking about pennies, energy, pick up where we left off yesterday. So, quick review. So you pick your initial and your final locations. Step 1, step 2, define ground zero, the lowest point you care about. That's ground zero. Step 3, figure out what type of energies we have. So initially we had kinetic energy. I don't remember how many pennies I drew. 5. Not good. I drew 6. All right. Do 6. Okay. And I had no potential energy. I'm at ground zero. So I'm moving. I'm at ground zero. Okay. So this is my checking account. This is my savings account. The total balance is I have 6 pennies in the bank. Okay. We discerned that there was no work being done by non-conservative forces, so that was 0. So what that means in the bank analogy is I did not take money out of the bank, nor did I put money into the bank. So anything that goes on is just an internal transfer. And then at the end, before we get to the end, so this is our initial state. This is our initial condition. This is the process, what happens between my initial and my final in terms of work being done by non-conservative forces. And then at the end, so I started with 6 pennies. I took nothing out, nor did I put anything in. So at the end, I still have 6 pennies in the bank. That's the second relationship. The third, so I look back and say, okay, where is the money distributed in checking or savings? And at the highest point, we determined that it's at rest, so there's no kinetic energy, so there's no money in my checking account. So there is potential energy, and it turned out to have all of the money because there's nothing in kinetic. So all 6 pennies are in the savings account. Okay, so it's just energy accounting. Okay, so that's where we left it, and we said that the change in kinetic energy, we got to here, right? I think we got here. Kinetic energy lost 6 pennies. Potential energy gained 6 pennies. Okay. If mechanical energy is conserved, then the change in potential energy will always equal the change in kinetic energy. One's lost, one's gained. It's just an internal transfer if mechanical energy is conserved. All the money's in there in the bank. It's just in different, arranged in different accounts. So now what happens if we incorporate friction? Does that change the energy I have initially? Not yet. So we're moving some speed at ground zero. So the fact that work is done does not change my initial conditions. Okay. But when work is done, you think friction is going to do positive or negative work here? Tell your neighbor. Positive or negative work done by friction. Okay. Negative work. Good job. I heard a lot of that. Bless you. So how much work? I don't know. I'm going to make this up. I'm going to say it does 2. It takes out 2 pennies. Okay, I'm withdrawing 2 pennies out of the bank. Bless you. So I started with 6 pennies in the bank. How many pennies do I have now? Good. Okay, I now have 4 pennies in the bank. I still have no kinetic energy. So how much potential energy do I have? Well, whatever is left, none of it's in the checking account's all in savings, but all I have in the bank totally is 4, so that means there has to be 4 in the savings account in potential energy. All right with that? So incorporating friction, see if you can figure that one out. Have a conversation. Okay, correct answer is A. Here we see kinetic energy lost 6, potential energy gained 4. Good with that? Here's an overarching statement. If there's negative work done by a non-conservative force, you're losing mechanical energy, and whatever energy is lost is going to be more than whatever energy is gained because you have less money in the bank at the end. I'll say that again. If you find out, if you discern that you're losing mechanics, like there's negative work done by a non-conservative force, then you have less money than what you started with. And whatever energy lost is going to have a bigger loss than whatever gained. All right with that? Okay. So these things are more of like the concept behind the energy. Let's do some actual math stuff. Okay. So remember how we had 5 steps with free body diagrams? Okay. There are going to be different steps, but if you walk through these steps, you'll be good to go. Step 1 is to define your initial and your final positions. So in this problem, throw a rock at 25 meters a second at 30 degrees off of a 10-meter high cliff. How fast is it going when it hits the ground? Okay. So my initial location position is going to be up at the top. Final location is at the bottom. That was step 1. Step 2 is to define where ground zero define where ground zero is. It's the lowest point we care about. For this one, it's kind of screaming obvious. It's the ground. Okay, so height is equal to 0 here. Good with that. Third step is to write out your energy, mechanical energy expression. Like, so you have kinetic energy initial plus initial potential energy plus the work done by non-conservative force is equal to final kinetic energy plus the final potential energy. This is kind of like what you're going to start with, and then we're going to identify what energies are present at those locations. Okay. So kinetic energy, you're asking ourselves, is it moving? Because the equation is 1/2 mass times speed squared. So in order for it to have kinetic energy, it needs to have a speed. Gotta be moving. Potential energy, you're asking yourself, is it above ground zero? Is it above ground zero? Because you need a height. Okay? So initially, do you have kinetic energy? Thumbs up, thumbs down. Initially, do you have kinetic energy? After it left your hand. After it left your hand. Yes, it's moving at 25 meters a second. Okay. So we do have kinetic energy. What about potential energy? Initially, do we have potential energy? Is it above ground zero? Yes. From the initial point to the final point, was there any work done by non-conservative forces? What forces are acting on it? Just gravity. Is gravity conservative force? Yep. So this, there is no work done by non-conservative forces, so that goes to 0. Okay. At the final, thumbs up, thumbs down for kinetic energy. Do you have it? The bowling ball hits your foot. Does it hurt? Because it's moving. You okay with that? It's not after it's embedded itself in the ground. It's like, and we're asked for how fast is it going at the end. The answer is not 0. You all right with that? Okay. So yes, we have kinetic energy. It is moving. What about gravitational potential energy? Nope, we're at ground 0. So this goes to 0. You all right with that? Okay. That step there is kind of like drawing a free body diagram. This is going to be our original equation for this scenario. Okay. So once we've eliminated the energies we don't have, then we come up here and we just substitute these expressions in. So we have kinetic energy is equal to 1/2 mass times speed squared initial plus potential energy is equal to mass times acceleration of gravity times height. I would not recommend writing this. I'm just trying to teach. That's 0. It's equal to 1/2 mass times speed squared final plus 0. Good with that? All right, so maths folks, what can I do to simplify this expression? I mean, we can do this. Larkin, what would you say? Okay, notice you have a mass in every expression. If we divide by mass on both sides, I can get rid of the masses. Okay, you can do that trick if there's mass in every expression. Okay, so then we're left with 1/2 initial speed squared plus gh initial is equal to 1/2 speed squared final. And now we can plug stuff in. And how many unknowns do I have? That's a pretty beautiful thing. I just got to do some math now. Like, it's not even crazy math. It's just, I don't have to do, not like moving things all over the place. It's just like right there. I'm going to jump up here, run out of room. Oops. How do we do? Not too bad. All right. A couple things I want to bring out with this example. Number one, what do we do with the 30 degrees? Nothing. That seems kind of Wrong. Does energy have direction? So it doesn't matter what angle I launch it at. That's a direction. Doesn't matter. Like, think about this trying to do projectile motion. Like, you would totally have to incorporate that angle. You'd have to find the components, all that stuff. Okay. If all you're looking for is how fast it's going at when it hits the ground, working energy, definitely an easier way to go. Now, if you're looking for where it hits, like the location, then you got to do projectile motion. Okay. So that's a cool feature. Secondly, what do you think this means in real life that the mass cancels out? Does that mean the rock is massless? Like, that seems kind of not right. Okay. Right. As the rock fell, the mass at the initial is still the mass at the end. That is true, but there's a more profound meaning behind this. What this tells us is it does not matter the mass of the rock. A rock will be going 28.65 meters a second if it was a 1 kilogram rock or a 5 kilogram rock. It doesn't matter. Think about this. In projectile motion or in free fall, if you dropped a bowling ball or a feather, it doesn't matter which one's more massive if we take away air resistance. Doesn't matter. Penny, feather, or tissue paper, the mass of it doesn't matter. Here, the mass of it doesn't matter. It's independent of the mass. It has mass, yes, but how much that doesn't. It doesn't matter. It's independent. Good with that? All right. Any other questions on this? Okay, I'm going to do the bar charts here. Okay. Again, I'm going to make up some numbers. I'm not going to try to take these numbers and fit them in here. It's just like, essentially, this setup here, step number 3, and this are just different sides of the same coin. Okay. So initially, I have kinetic energy. How much? I don't know. Not very much. I don't know. 1, 2. I'll give myself 2. That sounds good. Sure. Why not? Does it have gravitational potential energy? Yep. Yeah. It's probably a lot. I don't know. 4, 5. Sure. I don't know. Making that up. But here's where I'm not making up. This is my checking account. This is my savings account. My total money, my total balance. 1, 2, 3, 4, 5. That's a little different, huh? 6, 7. Let me draw those a little skinnier. Total money is 7. Okay. Got 2 in checking, 5 in savings. Total money is 7. There was no work done by non-conservative forces. So that means I ended up with still 7 pennies in the bank distributed somehow, some way. I didn't have any potential energy. I did have kinetic, so all the pennies are in kinetic. What was the change in kinetic energy? Gained 5 pennies. What was the change in potential energy? I lost 5 pennies. Mechanical energy was conserved. The change in potential energy is going to be equal to the change in kinetic energy. One's going to be positive, one's going to be negative. Okay, it's just an internal transfer. Good? Questions before? Oops. So this is the recipe for energy problems. Okay, I just walked you through them. Okay. Maybe, hold on, let me erase that so you can actually see that and it can be recorded. Okay, so those steps there. And then that's the bar graphs. Okay. All right. 500 kilogram roller coaster is going 1 meter second at the top of a 20 meter tall hill and plunges down, races back up a loop. How fast is it going at the top of this 15 meter high loop if friction does negative 3,000 joules of work? All right. Step number 1. Define your initial and final location. So go ahead and mentally pick those two. Initially and finally. Good. Step 2. Define ground zero. Make ground zero the lowest point that you care about. Ready for this one? This one's a little tricky. The lowest point that I care about between these 2 points is this one right here. I'm going to make this ground zero. Okay. All right with that, but it goes below. Like you can't. Yeah, it does, but I don't care. Okay. It's the lowest point that I care about between the initial and the final. All right with that? Okay. Step 3 is to identify what energies we have present. Okay, I'm going to give you like 30 seconds to figure out which ones are there and which ones aren't. Okay, initially you are moving at 1 meter a second. You are above ground zero. There is work being done by a non-gravitational force of friction. You are moving. I really hope you're moving. Okay, and it asks for how fast, so that's kind of screams the fact, hey, I should still have kinetic energy. And I am at ground zero because I made ground zero right here. How did we do? Okay. All right. That's, in my opinion, the most important step. So we write out our equations. Can I cancel out mass? Thumbs up, thumbs down. Okay. I don't have mass in this expression here, so I cannot cancel it out. Okay. So at this point, I plug in numbers. So I got 1/2 500 kilograms times 1 meter per second squared plus 500 kilograms times 9.8 times, initial height. Should I make that 20? Should I make that 5? Should I make that 15? So height is the height above ground zero. Here's ground zero. So this is my height. Are we good with that? So watch that. That's a important detail. Okay. Work done by friction is negative 3,000 joules is equal to 1/2 500 kilograms times final speed squared. How many unknowns? Just one. So that's a nice thing. So I just do some math here. How do we do? Any questions there? Not too bad. Okay. Last thing, I want you to do the bar charts. Give it a shot. Your numbers are going to look a little different. Do not try to incorporate these numbers into the pennies. The pennies are purely symbolic. Okay. So Okay. Again, the numbers I'm going to use are probably going to be different, but the relationships are the same. So kinetic energy, it's not going very fast. I'm going to give it 1 penny. Potential energy, I'm going to give it 4 pennies. Doesn't really matter. You could do more or less. But here's what does matter. Your checking plus your savings gives you your total balance in your bank. Okay. So for me, I had 1 plus 4 has to give you 5. You might have some different numbers. Okay. So that's your initial relationship. Secondly, we did, there was work being done from the initial to the final. So it was negative work. So I'm going to take 2 pennies away. Making that up. Okay, it's negative work. So at the end, afterwards, my final state is I only have 3 pennies left. Okay. And I don't have any potential energy. I do have kinetic. How much do I have? Well, all my pennies are in my checking account. Okay. So the follow-up to that is kinetic energy gained, potential energy lost. Which one experienced a greater change? Potential energy lost more than kinetic energy gained because we took energy away. We spent some money. Good at that. Call that good for today. Got a worksheet due on Monday.